Hello, this is Prof. Nanius. What I want to do today is talk about linear differential equations, just a brief overview for those of you who are taking our differential equations course and have had a course in linear algebra. So we'll just do this right here. So, I again, I'm trying to exploit some of the stuff you may have learned in linear algebra. So, the first thing I want to talk about is something called operator notation. Now take the following differential equation. Let's say you have y double prime plus e to the x y prime plus, um, let's say 3y, and let's make that equal to 0 for now. And I realize this could be just some function of x, but I'm going to call it 0 for simplicity. Well, the way you can think about this is you can think about this as an operation. The left-hand side, you can start with a function of y, multiply it by 3, add, take the function of y, differentiate it, multiply by e to the x, plus take the function of y and differentiate it twice. So in operator notation, you can write this as d squared. That's the operator that takes the second derivative. This operator here is it takes e to the x and multiplies it by the first derivative, d to the first part. And the third part is just the multiplication by 3 operator, and you apply y to it. So expanding, this is d squared y plus e to the x dy plus 3y, it still is 0. And d squared means take the second derivative. E to the x times dy means take the derivative and multiply by e to the x. And this says takes a regular function and multiply it by 3. So that's how operator notation works. Let's do a second example that I've talked about in class. In class, we've talked about this one here. Let's say y double prime plus 9y is 0. This in operator notation could be d squared plus 9 operating on y. Okay? Now, here's the thing here. Now, you can use operator notation if you have some function of x instead of 0. So for example, suppose you had y triple prime plus 3y double prime plus tangent of x y prime plus 4y is, say, log of x. This thing could be written as d cubed plus 3d squared plus tangent d plus 4, all operating on y, equals natural log of x. So that works as well. That works as now. And this might be a definition of linear. A linear differential equation or ordinary differential equation, since we're using regular derivatives, is one that can be written in, this is linear operator notation. Okay, where you have this linear operator hill, this thing here, we're just going to call this whole thing L, and this is L of y equals some function of x. Okay, now what's special about that? And this is where I think we're going to go to your knowledge of linear algebra. But the very first thing you would understand here is this. Let's go back to vector spaces. And let's say the vectors are differentiable, are infinitely differentiable functions, or I'll just say sufficiently differentiable functions. Why? And scalars, these will be, say, the real numbers. Although in some applications, you can use complex numbers as well. But reals, complex, or, complex numbers are fine. Then the first thing you realize is that if you have any function, or let's say, may as well have differentiable functions, but suppose you have g of x, and let's look at the nth derivative operator, and suppose you apply it to alpha y1 plus beta y2, where alpha and beta are real scalars. Well, this says, first of all, you take the nth derivative. Well, you've learned that the sum of the derivatives is a derivative of the sums, and these are scalars. So this will be this. Dn y2. And then we can multiply through by g of x. Um, and what we can do is we can bring this inside. So this will be dn alpha y1 times g of x plus g of x dn beta y2. So what we've learned is that this property here, that you can take any linear combination, apply this operator, and you get the sum of the operators. What this tells us is that this thing here, first of all, g of x, the operator, is a linear transformation. And two, the sum of linear transformations is a linear transformation. Now, if you remember your linear algebra, this is what's sometimes called the dual space. So the bottom line is that if you have if you have one of these operators, and let's just write a generic operator. So if you have a generic operator, let's say a n being some function involving x, nth derivative plus a n minus 1 of x times the n minus first derivative, all the way down to a1 of x d plus a0 of x. As an operator, this is a linear transformation. And that what that means, therefore, is if the solution to this, so if we set equal to 0, like here, the set of functions that make the 0, or that solve this, is called the kernel. The kernel of the linear transformation. And you learned in linear algebra, the kernel, or the null space, is a vector subspace. And what that means is that if you have two functions that are in this kernel, you can take any linear combination of them and they will be in this kernel. That's the first thing. Second, you'll learn about dimensionality. And if you have, let's say for let's say n, if you have n linearly independent solutions, and that linear independence means the same thing you did in linear algebra, that are all in the kernel, they span. That's a basis for the kernel. And what that means is all solutions to this can be written as a linear combination of functions in the kernel. Now let's just give you a quick example and then I'll leave you alone. So example, let's look at the operator d squared plus 9. And let's just try to solve this. Now, this corresponds to the differential equation. Now we learned in class, as note that cosine of 3x solves this. And we also know that sine of 3x solves this. Now, we haven't proven to you yet, but we will show, we haven't gotten there yet, that cosine of 3x and sine of 3x are linearly independent. Meaning that if you have, well, what that means is if you have alpha cosine 3x plus beta sine 3x equals 0 for all x, then alpha and beta are 0. In fact, I think I can show you that right now. So suppose you have this is equal to 0. And by the way, this is not how we're going to do it in class, but I'm going to do it here. So let's look at x equals 0, because this has to be true for all x. And then we get alpha cosine of 0 is 1, plus beta times 0 is 0. So alpha is 0. Now let's look at x equal, how about pi over 3? Then notice you get alpha cosine of 3 of pi. Well, that was stupid. I didn't mean that. I meant let x equal pi over 6. Now cosine of 3 times pi over 6 is cosine of pi over 2, which is 0. So if this is 0, we get alpha times 0 plus 3 times pi over 6, it's sine of pi over 2, times beta is 0. Sine of pi over 2 is 1, so beta must be 0. Now this was sort of a kind of a dorky way to do it. We're going to have a much more sophisticated way of doing this later in our course. For those of you who are seeing this outside my course, that's where Wronskians come in. We don't know what a Wronskian is yet, though. So anyway, what it says is that these two functions are in the kernel, and they're linearly independent, and we will show that this space is two-dimensional. So what that means is all solutions are of the form A cosine of 3x plus B sine of 3x, and there are no other. So that's how a brief way of how you can use linear algebra in some of this. This is just scratching the surface. There's much more you can do, but I'll stop here.